Hello, Mr. Betts here. As we get deeper into Unit 10, we're going to be looking at different ways that we can determine whether a series converges or diverges. So remember, a series is going to converge if, as n goes to infinity, as we add more and more and more terms, the partial sums are approaching some particular value. And we're going to start with what's called the nth term test for divergence. And so what this says is that if the terms are not approaching zero, so the terms that we're adding together are approaching some other number besides zero, or they're bouncing around between different values, then the series has to diverge. And the reason for this is the partial sums have to be approaching some particular value as n approaches infinity. So essentially we're looking at a limit that says the limit as n approaches infinity of the partial sums gives us the infinite sum, if this limit exists. Well, if the terms themselves are not approaching zero, then the partial sums are not going to be getting closer and closer and closer to one particular value. So based on that, we have this nth term test for divergence, which is a pretty simple thing. Essentially what it says is exactly this. If the terms don't approach zero, the series diverges, we're done. If you remember from doing logic in geometry years ago, we had something called a contrapositive. So this is a conditional if something, then something else. So if the limit isn't zero, then the series diverges. That's logically equivalent to what we call the contrapositive. If not the conclusion, then not the hypothesis. So this statement right here, if the series converges, then the terms are approaching zero, is logically equivalent. Not as useful to us, because usually the question is, does the series converge or diverge? But also the nth term test for divergence, just the contrapositive of that, which has to be true. We do need to be careful that we don't assume that the inverse is true. So the inverse is what we get if we just negate both the hypothesis and conclusion here in our conditional. And so a lot of people will assume that if the terms do approach zero, that the series has to converge. And I'm going to use an example, a very common example that's called the harmonic series, to show that we can have a series where the terms get really, really, really small, but the sum still grows without bound. It gets as big as we want it to be, even though the terms are approaching zero.